Hi guys. Okay, so we are going to look in this video, chapter 2, atoms, molecules, and ions. And I'll walk you through the PowerPoint slides from section 2.1 and 2.2. So we will look at the early ideas in the atomic theory and the evolution of atomic theory. For sections 2.3, 2.4, 2.5, 2.6, and 2.7, we have other videos made that can be watched. Okay, so first of all, let's look at the first thing is that, as we know that the chemistry is the study of matter, and every matter is made up of some kind of particles. So where did this thought evolve, or how did we come to know about the structure of atom? So the early ideas in the atomic theory, the main postulates are by Dalton's atomic theory, and I mean, there we will discuss here in this section, we will discuss Dalton's atomic theory, and then we'll also look at the laws that explain the multiple proportions and the definite proportions. Okay, so first is the early ideas. So the early concept that there is the smallest particle of an element or a matter, and that is called the atom, and that is indivisible. That concept came from the Greek philosophers Leucippus and Democritus. That was in the 5th century BC. Later, Aristotle and the other believers, they believed that the matter consisted of the other elements, according to them, were fire, earth, air, and water. Okay, so these were the basic things of which the matter was made up of. That was a belief of Aristotle. But John Dalton, who was an English school teacher, he proposed the atomic theory in 1807, in which he stated that the matter is composed of exceedingly small particles called atoms. These atoms, they have very definite properties, and these are the ones that participate in the chemical change. So for example, if you take aluminum, right? Aluminum, what are the properties of aluminum? Aluminum is shiny. It is like silvery, white, and it is metallic. It makes that crinkling sound. It has a very high boiling point. It has a very high melting point, and it is solid, right? And it can conduct heat. So these are the basic characteristics of aluminum when you look at it from outside, like the physical properties. But chemically, yes, aluminum can react with oxygen, aluminum can react with, bromine, chlorine, iodine, anything. And that produces another substance, and that's a permanent change, that is a chemical change. So Dalton kind of had an idea that if you take scissors and if you start cutting aluminum into small parts and small parts and small parts, and the absolute smallest particle, obviously, for now you would be able to see it by your eyes, but would still contain the physical and the chemical properties of aluminum, that smallest particle would be called the atom. Okay, an element consists of only one type of atoms, but the compounds will contain only one type of molecules. So the small particle of a compound is molecule, the small particle of an element is atom. So the mass of the atom is very characteristic of that element. So not just the physical and the chemical properties, but there is a certain number that is associated with the atoms. That number is the mass number and the atomic number also. So the elements that contain the atoms, very specific atoms, all those atoms will have a very specific mass, will have a very specific, mass number and the atomic number, and very specific, physical and chemical properties. Okay, atoms of one element differ from the properties from the atoms of other element. So the element that is of, let us say, gold is very different from the element of that's a silver. So we know it by our experience in life. Iron, for example, all the atoms that make up iron are different from the atoms that make up silver, and the atoms that make up silver are different from iron and of gold and of anything else. So atoms are very unique to the elements. Okay. Next is a compound consists of atoms of two or more elements combined in small whole number ratio. So these atoms, they combine with another atoms in very definite ratios. Okay, and these ratios are depending upon like how many bonds they can form or what is their capacity to make the bonds. So you must have heard the word valency. So that's where it comes from that. So it is always in a very whole number ratio. So full whole atom is going to combine with another full whole atom. Yes, one atom can combine with two atoms. Okay, yeah, I'm sorry, this is the daytime I'm recording, and I have a crow that keeps on crowing outside, so just bear with me here. But anyways, here, so in a compound, we will see atoms combined in a very definite ratio. Okay, and so the number of atoms of each of its elements are always present in that same ratio. For example, water. Water is made up of two atoms of hydrogen and one atom of oxygen. No matter where you find the water on this earth, whether it's coming from the ocean or a sea or a lake or in your home, a faucet in your home, or you're manufacturing it in the plants, doesn't matter. It's always 2:1 ratio of hydrogen and oxygen. That gives you water. You drink, and that when you drink it, you're able to live or survive, right? On the other hand, if you take two atoms of water and you combine two atoms of oxygen, that is going to produce hydrogen peroxide, which has completely different properties than that of water. Okay, so this 1:1 ratio and 2:2, in other words, 1:1 ratio, and the other one is 2:1 ratio, give those molecules with very specific properties. Okay, so this is all was known or understood, and all that came through experimentation and you know, just some of it is common sense, some of it is speculation, those things. Okay, atoms are neither created nor destroyed during a chemical change, but they rearrange to yield a different type of matter. So what is a chemical change? Chemical change is basically a permanent change in which the atoms of the starting material, they rearrange and they form a new substance with the totally different properties. So the mass on the reactants and the product side remains the same. Okay, now in this slide, what do we see? We see these pennies made up of copper. Okay, so if you take a penny and you break up into smallest and smallest, so you're going to find it is only made up of only one type of particles which retain all the properties that you see in pennies. Okay, so this is the copper atoms, and again they are arranged in a very specific pattern. The smaller the atoms, the more compact they will be. The bigger the atoms, the more, you know, spread out their arrangement is going to be. Okay, next is the when they combine. Okay, so when copper and oxygen combine, they form this a molecule, right? This is a copper oxide molecule, and this is copper 2 oxide. So copper and oxygen combine together, and now neither the new substance is brown nor the new substance is red. So here we see the browns are the coppers and the reds are the oxygen. So oxygen and carbon, when they mix together, when they combine together, new bonded state, they produce a new substance, which in this case is a black powdery compound, which it has a totally different properties. Neither it is metallic, like this is a metal, copper metal. You guys have seen copper metal. Copper metal is brown colored, and it's metallic. It conducts electricity, it conducts heat, it has a high boiling point, has a high melting point. Okay, so this copper is very like a copper wire. You've seen it. So this copper has one property. Oxygen is a gas. You can't even see oxygen, right? But when the two mix together, they produce this black powder, which is neither a good conductor of heat nor a good conductor of electricity, those things. So it has a totally different properties. Okay, so here's what the same thing is shown here. Oxygen in the jar, copper right here sitting in the base. When the two mix together, a compound is formed, copper 2 oxide. And here, copper and oxygen mixed in 1:1 ratio. So then that's what you get, copper 2 oxide. Okay, so Dalton's atomic theory, when we look at the law of conservation of matter is the matter cannot be created, matter cannot be destroyed, but matter is always transferred from one form to another. A new substance is formed with the new properties, but it's just through the rearrangement of atoms. Okay, so that's the microscopic explanation of the Dalton's atomic theory. Now, when we talk about chemical reactions, we look at it, okay, the starting materials are written on the left-hand side, the products are written on the right-hand side. What things are reacting are shown by the plus sign. The arrow shows the products, okay? But the arrangement is always very specific. The total mass remains the same. So here you have 4 atoms right here of the starting material, and you have 2 atoms of this, another starting material. When they form the products, fine, this bond breaks, and this bond breaks, and this bond breaks, and in a rearrangement, now you see the blue is in between the 2 greens, blue in between the 2 greens. However, the total number of blues is the same, the total number of greens is also the same on the reactant and the product side. So that's the law of conservation of matter. When you take the weight of this guy and this guy and this guy and this guy, so you add it. So let's say this is 4x and this is the 2's. You add these 2. So this is like 2y's. So this should be, the total is still the same on either side. Okay. Besides that, we also have another law, which is called a law of definite proportion, and the law, or it's also called a law of constant composition. Definite means very definite. Copper and oxygen, when they mix together, 1 atom of copper and 1 atom of oxygen will combine together to give you cupric oxide or copper 2 oxide. So that 1-to-1 ratio, very definite, that gives you that particular property. But yeah, copper, like 2 atoms of copper can also combine with 1 atom of oxygen. And when that happens, a totally different compound is formed. It is called cuprous oxide. So 2 different compounds, different properties. However, the ratio in which oxygen and copper combine for that particular compound is very definite. Okay, so all of the samples of the pure compound contain the same elements in the same proportion by mass. So this law of definite proportion was illustrated by Joseph Prout. So obviously they do a lot of experiments, you know, and they come up with that. So what do we see here? We see the constant composition of isooctane. So it is made up of carbon and hydrogen. Okay. Now, if you take these samples of isooctane, and here you see 1 sample, 2nd sample, 3rd sample, in which they have, through the elemental analysis, and so they found out that carbon is 14 grams in sample 1, 22 grams or so in sample 2 in B, and then 19.4 grams in sample C. Okay, now hydrogen, and this is another hydrogen. Hydrogen is 2.78 in sample A, 4.19 in sample B, and 3.64 in sample C. Okay. Now, when we look at the mass ratio, you're going to take carbon over hydrogen. Okay. So we see that for every 1 gram of hydrogen, there is 5.3 grams of carbon in all the 3 samples. So in other words, if you want isooctane, the ratio should be 1 gram per 5.3 grams of carbon. Only then you can get this molecule. That's the minimum, that's the ratio, the combination. Obviously, you know, you would need more hydrogens and oxygens, but that's, you know, there is an empirical formula and a molecular formula. We will discuss that later, but that's the simplest whole number ratio. Okay. Now, I mean, as you know from your previous, that 1 gram of hydrogen will contain, like actually the experiments are at the atomic level. So the 1 gram of hydrogen will contain, 1 gram of hydrogen will contain like several atoms on of hydrogen, and same story with carbon. So, but that's the mass ratio. Okay. So let me see if I can remove, get that crow off from the outside. So give me a minute. Okay, sorry about that. Okay, so here we have the law of multiple proportion. The law of multiple proportion states that when 2 elements react to form more than 1 compound, a fixed mass of 1 element will react with masses of the other element in a ratio of small whole numbers. Okay, so in this case, for example, you have chlorine and copper. So here, copper can form, here's another thing, a little bit more at the microscopic level. Copper can form one bond and copper can form two bonds. In other words, copper has the capacity to combine with only one chlorine. And in that case, it is going to form copper 1 chloride or cuprous chloride. And here, this is green colored. The salt or green colored compound is formed. So the green solid contains, that's by the mass, that's just a ratio, per 1 gram of copper, we find that the amount of chlorine is 0.558. Okay, so that's one piece. Next is when you put more chlorine on that, then fine. Copper extends its capabilities and copper can combine with 2 atoms of chlorine. So here, this gives a totally different substance, and that substance is brown solid, and the name is copper 2 chloride or cupric chloride. So in this case, we see 2 atoms of chlorine in 1 atom of bondage to 1 atom of copper. So the mass ratios are 1 gram of copper contains 1.116 grams of chlorine. So now in this, the difference between the 2 compounds is, we see the first one is containing 2 atoms of chlorine, the second one is containing 1 atom of chlorine per 1 gram of copper. So 2-to-1 ratio. So this is called a multiple proportion. In other words, atoms can, it depends, you know, what the atom is. Sometimes the atoms can combine in more than one different way. And when that happens, a totally new substance is formed. Think of it, example, copper combining with one oxygen makes carbon monoxide, but copper, I'll repeat that again. Carbon combines with one oxygen and makes carbon monoxide. Carbon combines with 2 atoms of oxygen will make carbon dioxide. So both the gases are totally different. Okay, so in this case, we see that the copper and chlorine are combining in different ways, and then same is the case as I talked about, copper, carbon and oxygen combining in different ways, and so forth. So this applies to a lot of elements, a lot of atoms, you know, they have a capacity to make more than one type of bond. So we will look into that as we move further, but here, this is the copper 1 chloride, and this is with copper 2 chlorides. Okay, so that's the colors are also different. Okay, next is the evolution of the atomic theory. How did we come to know about the structure of atoms, and like, you know, what is an atom made up of, and how did we actually like validate that structure? So in this case, we are going to look at the different experiments by Thomson, by G.G. Thomson, Millikan, and Rutherford, and then, so we know that atoms are made up of, now, of course, nucleus in the center, and that nucleus contains protons, positively charged, neutrons, neutral charge, and electrons are around the nucleus. Okay, so that's the basic 3 subatomic particles. But how were they discovered? Okay, we will discuss some of these key developments. So here we have Sir J.J. Thomson. He did his experiments in a cathode ray tube. So the cathode ray tube looks like this. So what is that? Here you have the cathode, which is a negatively charged like an electron. Anode is a positively charged electrode. Okay, and this whole tube is sealed. Sealed means nothing can go inside and nothing can go outside, and there is nothing inside. It's a total vacuum. It's a complete vacuum. Okay, so here we have the magnetic field, and that's battery, magnets, and some kind of a detector is here. So now what we noticed that when we passed the electrical current, okay, whatever the cathode was made up of, it didn't matter. Every time we saw a ray pass through and it got deflected, ideally it should have gone straight. There's nothing inside the vacuum. There's nothing inside this container. This is his original, you know, piece, but there's nothing inside it. So there's to prevent it, it should go straight. But when it went from a negatively charged these cathode, when they passed, so some rays, some particles were being emitted from this electrode. And these particles had a charge. These particles must be negatively charged. So that is why they got attracted to this positively charged anode. And then when they passed through the electrical current, and then there's a battery, they got attracted to the positive end. And that's how they got deflected. So they got attracted to the positively charged, site in this container. So that means some tiny, tiny, tiny particles were being emitted from the electrode. And whatever the cathode was made up of, it didn't matter. The results were always the same. So he came up with the discovery of these negatively charged particles called the electrons. These particles are much lighter than the atoms, very light, lighter than the atoms. They are negatively charged, and they are indistinguishable. In other words, no matter what the source of the material was, all of them behaved the same way. They all had the same properties. So it is not like these electrons are coming from gold, or the electrons are coming from silver, or the electrons are coming from let's say like iron or copper or zinc or nickel. It didn't matter, right? They were all the same. So the cathode ray particle is what we now call the electrons. A negatively charged subatomic particles means it's a small part of the atom with a mass more than 1,000 times less than that of an atom. So it's a very, very light thing that is present in the atom. And so we discussed that, and that was like the conclusion. Okay, then Robert Millikan said, okay, fine, it seems that these are really tiny particles, and now we need to know, if we could know the mass and if we could know the charge, then that will be great. So charge to mass ratio, Robert Millikan, he discovered, and his experiment was based on the oil drops. And now what does the oil drop experiment look like? Like this. This was a structure. This is like his setup. So what did he do? He put like a very tiny, like this is like a electrically charged, brass plate here. And in that, there are like really, really tiny, tiny holes, very tiny holes in that, really tiny holes. And he sprayed oil droplets on top, right? And oil atomizer, like really tiny droplets of oil. And we wanted to see, we know it, like, for example, things get charged. If you rub your hand, and then you touch your hair, or if you touch the wool, or if you touch the fabric, you see like a little strands, they rise up. So that means that something has been charged. There's something charges there. So that's what he was trying to do. He was trying to pass the oil through the holes in the brass, like sieve, like a mesh. So when the oil rubbed against the brass holes, it kind of got charged. Then there was like a telescope, an eyepiece, a very interesting one. And then there was X-ray to produce the charge on the droplets. This was also another thing that was done. So anyways, the charged oil droplets, when they fell with a certain speed, right? And when he was able to measure that, and he was able to measure the charge. Now, all this is again very, like at a very higher level, but just so you know that these were the experimental, methods were used. And he found that the charge in coulombs on like a single electron is about 1.6 into 10 to the power minus 19 coulombs. And then the rest, he also found that the more the X-rays were passed, or the more they got like friction came in and so forth. So they found that the charge was in some kind of a, like the other pieces also had some charges, but they were in certain like whole number ratios, or in some numbers, some whole number. Like for example, here, 16 twos are 32. So in other words, like roughly, so this was so if D droplet had +1 charge, B had +2 charge, right? And A had +3 charge, and C had +4 charge. All of them were the same charges, but it just, you see these numbers, they are just in some ratio was there. Or so we said that, okay, there could be one electron, or there could be more electrons, there could be less number of electrons, and it was always a whole number. Okay, so that's another thing, that substances can have more than one charge. Okay, so he concluded that the charge on a single electron, Millikan's experiment concluded that the charge on a single electron is 1.6 10 to the power negative 19 coulombs, and the charge will always a multiple, the charge on the oil drops was always a multiple of a specific charge. Okay, and then Thomson already showed the charge to mass ratio of an electron to be 1.759 into 10 to the power 11 coulombs per grams. So the mass of the electron they calculated comes out to be 9.107 into 10 to the power negative 31 kilograms. Okay, so that's one thing. Next is we're saying, okay, where are the electrons now? Initially, they had this plum pudding model in which, you know, these pudding, and then there are plums or raisins or even chocolate chip cookie. So those things that the electrons, if there is a negatively charged electron, there has to be a positively charged, you know, surface or space, or some positively charged, you know, entity should also be there in a molecule, in this atom, sorry. So that was one initial model. Then Nakaoka, he said, no, the structure of atom is like that of the, like Saturn. Okay, so these rings, these electrons are present in the rings, and there is some central piece where the positively charged particles are there. Then Rutherford said that, okay, let us determine these positively charged particles. Where exactly are they? Are they spread out like in a plum pudding, or they like a Saturn and the rings? Where are they present? Okay, so Ernest Rutherford, he came up with his gold foil scattering experiment. So here is this gold foil scattering experiment in which he put radium as a source of alpha particles, positively charged. Okay, and then this piece right here is the luminescent screen to detect the scattered particles, or some kind of a detector. And he put a gold foil. So, you know, gold foil, because gold is, this has like a bigger atoms, larger mass number, right? So gold, and then besides, gold can be made into very, 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 very thin sheets. Now we are trying to see, you know, what is microscopic level, what is inside the gold foil, and we're trying to kind of figure out like the structure of atoms of the gold. So here we take this extremely thin gold foil, put it in the center, and we bombard it with the beam of alpha particles. Now what do we see? Yes, majority of the particles, now these are big particles, these alpha particles are pretty big. When they passed through the gold foil and they went straight. So most of the alpha particles went straight. Okay, they did not like move anywhere. So nothing was blocking them. And of course, this is a gold foil, it's still a solid. But a few of the alpha particles, when they hit the gold foil, they got deflected. A few of them slightly deflected at certain angles. But some of them, when they hit in the gold foil, some of them got deflected like at a bigger angle, a larger angle, or kind of like, you see that, like they hit it and then they went, you know, like at a different angle. So in other words, they didn't even pass through. These guys passed through. So this means that there is something inside the gold foil, which is obviously the atom, and there is a place in the atom in which this place in the atom, there is something inside the atom which blocked the path of a few alpha particles. So that is why they couldn't even pass through. They got deflected at a very, you know, significantly larger angle. But some of them did pass through, but they hit something inside, so they got deflected at like a smaller angle, but they did pass through. But majority of them just simply passed through. So what does this mean? What is the conclusion? So here the conclusion is that majority of the space in an atom is an empty space. A large majority of the space is an empty space. That empty space allowed the beam of alpha particles to pass through. Nothing blocked. But there is some solid also present in the atom. This solid has to be positively charged, because that is what causes the deflection in these particles. When these alpha particles hit right in the center of the solid, they got blocked. And because they were positively charged, they got repelled also. So that is how they got deflected at a very large angle. But the ones that barely touched the side or the corner or the periphery of the round object, something inside the atoms, and that is obviously the nucleus, but when it touched, they touched it, and then they got deflected at an angle. So that was the discovery of Rutherford's, that majority of the volume of the atom consists of an empty space. Then a small, relatively heavy and a positively charged body called a nucleus, it's the center of the atom. The nucleus consists of the atom's mass, the main mass, okay? The negatively charged electrons surround the nucleus. So obviously the protons are the positively charged species, the subatomic particles that are located in the nucleus, and it is the protons that give the charge to the nucleus, because of which the repulsion was faced by the alpha particles. So this is what the story is. So this is how it looks like. So when these guys came, you see that there's empty space. This guy's empty space. That is why they passed through straight. Nothing was stopping them. However, the ones that hit the center, boom, they got deflected at a large space. Or the ones that touched the periphery slightly, they changed a few alpha particles were slightly deflected. Okay, so that's at the microscopic level, or the enlarged cross section of copper. So other important discoveries were isotopes. Isotopes are the atoms of the same element, but with a different mass. Now remember that number of protons are the ones that give the identity to the atom. If the number of protons change, the identity of the atom changes. Number of electrons only give charge to an atom. Less electrons, positive charge. More electrons, negative charge on the atom. But the nucleus contains neutrons, which actually buffer in between the protons. And so they keep the protons bound in the nucleus, the neutrons. Neutrons have no charge, and yes, they are heavy. In fact, they're heavier than protons. So what's the deal with the neutrons now? The neutrons, they form the mass. But if the number of neutrons vary, the only thing changes is the mass of the atom. The actual identity of the atom, the properties of the atoms don't change. For example, hydrogen. Hydrogen has 3 isotopes. Hydrogen, just a normal hydrogen, contains 1 proton and 1 electron. No neutron. Deuterium contains 1 proton, 1 electron, but 1 neutron also. And tritium is another proton, is another isotope of a hydrogen, which contains 1 proton, 1 electron, but it contains 2 neutrons. So you see that neutrons make tritium heavier than deuterium. Deuterium contains 1 neutron. So that's deuterium is heavier than just the ordinary hydrogen. So the more abundant ones, hydrogen is the one with just protons and the neutrons, protons and the electrons, sorry. But the other ones, deuterium and tritium, are found in nature, but less amounts of them. So they are more like unstable. Okay, so neutrons were discovered by James Chadwick, and neutrons are also found in the nature. So neutrons are also found in the nucleus. So the nucleus consists majority of the atom's mass. Protons and the neutrons are much heavier than the electrons. Okay, electrons occupy almost all of the atom's volume. In other words, outside, like the empty spaces where the electrons are found. The diameter of the atom is really, really small. You see that 10 to the power -10, that's the magnitude, meters. And the diameter of the nucleus is 100,000 times smaller. That's 10 to the power -15 meters. So What does it look like? What does all this mean? So here's the thing. If you take these blackberries, you take one blackberry, just one blackberry, and you place it in the center of a football stadium. You see that? You can't even see that. But all this empty space, that is the space that is present. Like it has been, like it's an analogy. So that's that kind of picture if you can get. So that this is what it means, this diagram right here, where the nucleus is really tiny and it's in the center of the atoms, but all this empty space is like it's a huge empty space where the electrons are found. Okay, so so we have now the basic things, that the atoms and the subatomic particles are very small. The carbon atom weighs less than 2 into 10 to the power negative 23 grams. And again, this has been calculated and verified. Electrons have a charge which is less than 2 into 10 to the power negative 19 coulombs. And then the small units we use is generally atomic mass units. Okay, one atomic mass unit is 1.660 into 10 to the power negative 24 grams. So if we say carbon's mass is 12 atoms, or the atomic mass unit, so that means if the mass of carbon 12, so would be 12 atomic mass units. This was originally, we used that. So this is an old method, but now of course in our calculations we use the molar mass. Okay, the fundamental unit of charge we already talked about. The electrons have a charge. So here the electrons have a negative charge, the protons have a positive charge, and the neutrons have a zero charge. The mass of a proton is 1.007, mass of a neutron is 1.008, but the mass of electron is 0.00055 atomic mass units. Okay, so that's a very basic thing. Next comes the atomic number. What is the atomic number? The total number of protons in the nucleus of an atom is the atomic number. Okay, and this is what defines the atom. An atom that has 6 protons is always going to make carbon. Neutrons, the number may vary. Number of neutrons can change, but that is only going to change the weight. But the 6 protons are the ones that is going to give the characteristic to carbon only. If you bring 7 protons, then it becomes nitrogen, totally different substance. Now, when we say neutral atom must contain the same number of positive and the negative charges. Neutral atoms. So the number of protons and the number of neutrons are always equal. Okay, the atomic number is, what is atomic number? Atomic number is the number of electrons, and atomic number also means the number of protons. What is a mass number? The mass number is the number of protons plus the number of neutrons. Okay, so both of them combined together. So mass number, the mass number is the protons plus the neutrons. Okay, now if you need to find how many neutrons are there, you just take the mass number minus the atomic number, or the mass number minus the number of protons, or it's electrons also. That gives you the number of neutrons. Next is the ions. What are ions? Ions are the ones with the charge. There can be a positive charge and a negative charge. When the number of protons and the electrons are not equal, the atom gets electrically charged. The charge on an atom is equal to the number of protons minus the number of electrons. So if there are more, if the number of protons is more, positive charge. If the number of electrons is more, negative charge. Okay, so that's by losing or gaining electrons. Next is the cations and the anions. What are cations? Cations are positively charged, anions are negatively charged. So when there are, when an atom that gains 1 or more electrons, it will have a negative charge. And how many electrons are gained or lost, that depends on, the charge, that becomes a charge number. Cations is again an atom that loses 1 or more electron will exhibit a positive charge, and how many are lost depends, and that leads to the charges. Like for example here, example of sodium, it has got a charge of the atomic number is 11. Okay, if this atom loses 1 electron, then it becomes, then it has got now only 10 electrons. So it gets a charge of +1. Here you have a neutral atom of oxygen, which is the atomic number is 8. Okay, and if it gains 2 electrons, then it has got now 2 extra electrons. So the charge is 10 electrons total. So it has 2 negative charges. Okay, now we are going to look at the chemical symbols in the periodic table in the next video. And then, we will also look at the like the common periodic symbols. You need to memorize them. You need to memorize them. And then you're going to look at the periodic table. And in my next video, I'm going to be doing some of the learning check problems from this chapter. Okay, so I hope that was easy, and thank you for watching. Bye-bye.